Go for it.
All right. Good morning, everybody. Welcome to our joint session of OMUG and the ITE SimCap. I'm Garth Aponitis with DKS Associates, and I'm part of the coordinating committee with OMUG, along with Kyle Hauger and Winning Wang. The Oregon Model Users Group, or OMUG, provides educational and networking opportunities to expand the knowledge and cultivate the skills of Oregon's modeling professionals. And I'll provide some more information about our group at the end of today's meeting. In the meantime, I'd like to introduce Randy Johnson. Randy is a senior transportation engineer with DKS and leads their multi-resolution modeling discipline group. Randy is also the co-chair of Oregon ITE SimCap, the subcommittee, and a member of the TRB simulation committee. Go ahead, Randy.
All right, thanks, Garth. So just wanted to thank OMUG for teaming up with the Oregon ITE SimCap group here. And for those who don't know Oregon ITE SimCap, SimCap stands for the Simulation Capacity Users Group. It's actually, there's national chapters all across the US in different ITE districts. And really it's a group of folks who just want to get together, share ideas and project applications about all things data and analysis. So it's not just focused on simulation, it's really all levels of analysis. So there's a lot of overlap with the OMUG group here. And so DTA very much fits within a lot of the focus areas that we cover. In fact, one of our last sessions, last September, was focused on freeway and ATM applications with dynamic traffic assignment using AIMSUM. So look forward, you could go to OregonITE.org and see upcoming events that we have. We currently don't have any on the list. We just had one a few weeks ago. And so we'll be hopefully getting new events here on our website in the next month or two, most likely after summer. If you have any questions or want to make sure you're in the loop with the Oregon ITE SimCap group, feel free to shoot me an email. My contact will be at the end of my presentation that I'm going to give later, but up front here, it's rsj@dksassociates.com, and I'll be sure to get you on the email list for the ITE SimCap. So with that, let's go ahead and jump right into the presentation. So we have four presentations today. And so we're going to kick it off with Peter Bosa. He's going to be presenting on Metro's macro level DTA. And Peter Bosa is a principal researcher and modeler for Portland Metro, where he oversees the transportation model development and application. Peter has over 15 years of experience in transportation research and modeling application. Recent work includes several DTA deployments in the Portland Metro region, including the I-205 tolling study, interstate bridge replacement, and the upcoming West Side Corridor multimodal study. So Peter, I'll go ahead and kick it off to you for the presentation. You're on mute, Peter.
I know, so I got muted. Am I still muted? Okay, looks like I'm unmuted. And you can see my presentation, Randy?
Yes, you're good to go.
Okay. All right, excellent. Well, thank you. Thank you for having me, everyone. I'm gonna just spend a little bit of time today talking about our dynamic traffic assignment tools and application in the Portland Metro region. I know that the description said our macro scale DTA. I think that macro scale was meant more in terms of geographic spread. So the entire Portland region or large portions of the region, it's not necessarily a macroscopic DTA. But we'll get into that here in a bit. So, okay, so this is kind of where we'll be going. A little refresher on what is DTA, some of the history behind the development for Metro, and then we'll get into how we've been applying it, mainly what we do in terms of calibration, and finally, you know, some of the applications we've had here at Metro, and some Q&A if we have time at the end. Okay, so just a quick refresher. This is what I was referring to when I said macro scale. So we have a continuum of resolutions of modeling tools, right? When it comes to assignments, at one end, you have your macro simulations. These are often referred to as static assignments. They're tried and true tested assignment tools. They've been around for decades. They're usually integrated with your trip-based models. They do great for evaluating route choice capability. They run very fast on our computers, and they're kind of the workhorse of our long-range planning here at Metro. Some of the cons is that these tools will they'll assign all demand regardless of network capacity. So when you move into future years or even today in heavily congested time periods, these tools will assign the demand to the facilities regardless of the available capacity, and you can often end up with volume to capacity ratios that exceed 1, which an engineer would cringe at. They also, while they do a pretty good job of pinpointing where bottleneck locations might occur, they do not do well with simulating the queuing that occurs because of the bottlenecks. And so because of that, they do a poor job of capturing congestion impacts upstream from your bottleneck locations. And so they they definitely underestimate travel speeds. They overestimate speeds and underestimate travel times for very congested corridors. And then I have kind of a list of some of the common tools that are static assignments. At the other end of the spectrum, you have your micro simulations. These are very precise, highly detailed computer simulations. Often the vehicles are almost like agents. They're being modeled one individually. They can be assigned specific driver behavior, and they're being simulated in almost real time. So very small fractions of sometimes even sub-second. They're very time consuming to develop and calibrate. They take a lot of time in order to make sure they're functioning properly. They're computationally very intensive because you're modeling many more single individual objects. The vehicle paths are often fixed, not always, but the traditional application is you get a set of vehicle paths from something like a macro assignment, and then those paths are fed into the micro simulation, turned into individual vehicles, and then it's left up to the operator to determine how to deal with situations in which the demand coming out of your micro assignment might be too far exceed the capacity capabilities of your facility. And so they can sometimes overestimate the amount of congestion on a facility because there's not really that release valve of alternative routes to look at. I'm speaking in generalities here. I know that Chayton would probably, raise his hand and say, oh, wait, our tool has ways around that. But this is just, just kind of in general. Then you have this sweet spot, the Goldilocks spot, the meso simulations, dynamic traffic assignment. Occurs there are macro level macro scale traffic assignments, DTAs. There's some that act more like a micro simulation, but we kind of just group DTA in with this meso simulation description where you're modeling large areas similar to the macro assignments. You're simulating individual vehicles. There's even some generic behavior associated with some of those vehicles. They're capacity constrained, so you're never going to get a VC over 1. They do a great job of identifying bottleneck locations and the queues associated with those bottlenecks. And in general, they give us the opportunity to evaluate operational characteristics at a much larger scale than we're used to. Operational characteristics of your highway system. And so below is just a kind of a list of some of the products that are out there. We've been using Dynamec quite extensively in our region. It's but I've used all of these other tools that I've listed below, and they all have their advantages. So this isn't by any means a judgment call. It's just we use Dynamic in our region. So we've been actively engaged in DTA development here at Metro since basically for over a decade. Since like 2010 is when we really got going. We spent a lot of time and resources developing networks, actually all the way down to the lane and intersection level. So when we developed our first networks, we were adamant about getting turn pockets correct, turning movements for lane-to-lane turning movements and intersections, the length of turn bays, as much detail as we could possibly get into our large regional networks. And part of this was because there had been this promise for DTA out there for a long time. It's a tool we've wanted to use. Unfortunately, until the last maybe 4 or 5 years, I would say that the promise of DTA exceeded kind of the ability of the tools to function in a manner that was conducive to our planning. So basically what I'm trying to say is that the computational runtimes of these DTAs was significant. It didn't make them practical to run at a very large scale. And there were also some issues behind like convergence and all of that aside, we still found a couple of test cases where we could deploy these tools. The image here shows some of those deployments. There was as part of the Barber study, we actually did like a SHARP grant where we looked up. Somebody's unmuted real quick. Okay. And then we did one for, it looks like a rather large area. This was actually, sorry, the yellow one was produced as part of the division Foster study. And we actually PAL study, and you see this little red area here. This was actually the little DTA section that we ended up using, and it was integrated with a micro simulation. Okay, so after over the last couple of years, our developers have been hard at work. They've improved the assignment capability of their tools. There's multi-threaded assignments now. They took some of the more complicated calibration features like signal optimization and automated those. There's methods now for dealing with supersaturated conditions. So even if your demand exceeds capacities, the tools are able to kind of massage it in such a way that they can still reach convergence in a relatively reasonable amount of time. And they have the capability now to scale to much larger areas than before. So we started a project a few years ago trying to figure out what's the quickest way that we could deploy a DTA at a large scale. What are the features that are most important for a DTA? And we basically came up with this quick launch DTA idea with our friends at Inro, the developers of Dynamic. The whole idea was we wanted to simplify, standardize, and economize, basically take advantage of repeated applications of our DTA tools. And during this project, what we learned was that a couple key takeaways. One, it should be at the top. Ramp meters are really important across all the tools that we've ever tested for DTA. If you can get if you want to get your freeways validated well to observable data, you really need your ramp meters in there. They're critical for controlling the flow of traffic onto and off of your freeways. The presence of signals matters, not a surprise, but the actual timing plans are less important when you're looking at a larger scale. So generic timing plans seem to work fairly well. And so you don't have to worry about necessarily getting every signal timing plan correct in your model, which is great. And then we also found that turn-based didn't really improve our model validation, at least at a higher level. We do have lane-to-lane movements in our model. We do have turn-bay links, but we found that if needed, if we had to, we could use a tool that basically creates generic turn-based, standardized like 100 feet, determine the locations where they should go, put them in. And that seems to work just as well as having actual representative network, a real life representative network. We also did some work around how do we move from our trip-based model, which it produces the trip tables that feed the DTA. How do we move from that into the DTA? Our trip-based model is run at the regional level. We knew that the DTA, the final applications would tend to be at a sub-regional level. Does it make sense to go from a regional trip-based model to a sub-regional, to take a sub-area cut of those networks and then move those into DTA? Or does it make sense to take your regional trip tables, move those to a regional DTA, and then use that to take our sub-area cut? And we basically landed on the latter. Go from the regional DTA to a sub-area DTA, and I'll talk about that here in a second. So this is an example of an application for the I-205 project. In this project, we start with a regional DTA. We haven't optimized all the signals or anything. We're not too concerned about even validating well at the regional level. Instead, what we're doing is we're loading all of our static assignment trip tables onto the regional network, and we're just running it just to kind of get a capacity constraint on the demand in the network. So this way, when we do our sub-area cut, we know that the demand feeding into the sub-area won't exceed the carrying capacity of the network, and it helps improve our validation of the sub-area later on. There's an efficiency with reducing the demand to the carrying capacity of your network before you start doing your hardcore calibration and validation. This is just kind of an idea of some of the attributes involved with the dynamic product. It is lane-based. So you can see here, every facility, it is lane to lane. You can actually see the turning movements at intersections. And you can also see here, this is the phasing for the signal at the intersection. So there's a lot of detail in these networks, far more than in our static assignment networks. And this is what I was talking about, all the time that we spent coding those networks at the beginning. Okay, so this is just, these next two plots are basically just showing, they're from portal data on I-205, and it shows the relationship between speed and density on your freeway, and I think volume and speed and flow rate. And so I put these in here because they show what's happening in real life, and they also show what the DTA is doing. So in real life, this is a facility on I-205. As it fills up with traffic, it can maintain a pretty steady speed up into a certain point. You'll notice here, and our flow rate keeps increasing almost up to 2,000 vehicles per hour per lane, but not quite. I'd say maybe it maxes out at around 1,750, 1,800. But then we see a huge drop off in speed, and the flow rate starts to decrease. So what's happening here is you're filling up the facility with traffic. Because of that, the congestion is causing friction, slowing vehicles, and as a result, you get less and less vehicles through the corridor. So that's a primary difference between a DTA or micro simulation and your static assignment. The static assignment would show slowing speeds, but your flow would still increase. It doesn't have this ability to decrease flow as your congestion builds. So the DTA is basically capturing this as you reach a critical mass, your flow rate decreases, your speeds decrease, and that gets represented in the we'll see that in a little bit. So here's just some of the characteristics that we tried to validate against. We lifted many of these from the VISM protocol that was developed for ODOT, microsimulation protocol. Because this is a different tool than microsimulation, we're a bit more relaxed, especially when it comes to some of our GEH and other goodness of fit statistics. But you can see here that we're still trying to go for a pretty good fit, high R squared, low GEHs where possible on counts. The same with the travel time. This is actually something where we can be a bit more in line with the VISM protocols, where we look at the travel time calibration criteria that are set out there. So we try to match the travel times within the DTA to that that we've observed with INREX or HERE data, and we try to fall within the prescribed ranges. So within a minute for travel segments that are 7 minutes or so, and within 15% if it's longer than 7 minutes. Here's an example. So when we're calibrating our DTA, we're really looking at three things. We're looking at counts, we're looking at travel times, and then we're looking at these things are space-time plots, which show the relationship between speed and volume on your freeway. They're really good at capturing bottleneck locations. So here, for example, this is I-205 southbound in the AM near the Abernethy Bridge in Oregon City, West Lynn. This is the INREX data. As you can see, as the colors get darker, that means it's slowing. We see a bottleneck occurring right around 7 a.m., extending back almost to 82nd Avenue, at least through the 9 a.m. for the AM peak period. We see that here in the dynamic model as well. I think this shows that we've done a pretty good job of calibrating this model so that the bottleneck location is captured, and then the actual shape of the queue spilling back, the extent of the queue, the duration looks very good. This is another example where we feel like the dynamic model is doing the right thing and actually has there's better resolution than the INREX data. So the INREX data is much more general. The dynamic model shows the queue, I think, in higher detail. And then this is, once you've got your DTA established, you can start doing comparisons. So this is a 2015 base year. We already have congestion at the bridge spilling back in this corridor. By 2027, under a no build scenario, that congestion only gets worse. And by 2040, assuming a no build, we just have complete congestion in this entire corridor. And here's an example where we have done some analysis with a build scenario. We added capacity in the corridor. As a result, the bottlenecks have been alleviated, and you can see the queuing is gone, free flow speeds through most of the corridor. So if there's any takeaway, I'm trying to do a time check here. I probably have maybe 5 minutes, 2 minutes. If there's any takeaway, if somebody asked me, what's the biggest difference between the DTA and your static assignment, I would say that the biggest differences occur not in your scenarios where you've added capacity and alleviated your congestion. It's in the scenarios where you have a lot of congestion. So when you have a lot of congestion, the static assignment will tend to push more vehicles through a corridor and overestimate the speed at which they're traveling. The DTA, however, is capacity constrained. And so what happens in really congested corridors is you get much less throughput. So in this example, we're getting about 25% less volume through our no build scenario. You can see that our two build scenarios are quite similar between our static assignment and our DTA. And that's because we've added enough capacity that there's no longer bottleneck issues. And both models do a fairly good job of modeling that type of a condition. But in the highly congested time period, the DTA is more responsive to the congestion. We see much more diversion in our no build at slower times or longer travel times, slower speeds. So some of our applications in the region, appropriate application, sub-area and corridor level analysis of just vehicle traffic. So the DTA, while it can have transit vehicles in it, it's not doing an actual transit assignment, meaning there's not people walking to transit stations and boarding on the vehicles and continuing on. So this is a tool right now that's just meant for vehicle traffic. It's great at studying capacity changes, maybe some operational changes related to signals or metering. And we've been using this tool extensively for looking at pricing in our region. They're great for identifying maybe intersections for mitigation analysis. They're time period specific, so that is a shortcoming. You have to develop these models for specific time periods. So like an AM peak or a PM peak, they're not all day. And moving into the west side study we have coming up, we'll be looking at potentially ways of using DTA for local air quality analysis. What we have found right now, not practical for full regional implementation. There's no feedback mechanism with the travel demand model, so we're not going to see mode shifts related to the DTA. It's not going to be feeding into that. There's no transit component to the DTA. So it's more time and resource intensive to establish than our regional travel demand model. There's much more calibration time, it's more akin to a micro simulation than a static assignment when you're talking about calibration time. You have to calibrate each application of the DTA, and you have to calibrate each time period being modeled. So this adds time. And frankly, at the end of the day, this just becomes another tool that supplements the rest of your tools. So this is a tool to supplement our regional travel demand model, not replace it. And so a couple of the projects that we're using this on, the I-205 studying project, looking at pricing, the tolling study, the interstate bridge replacement, RMPP, which is a large pricing project, and then the upcoming West Side Corridor multimodal study, which is US 26. And I'll take questions if there's time. I apologize if I went over my allotment.
No, you're good on time. We have a few minutes. So if anybody has questions, either drop them in the chat, or I think the group is reasonably sized here. Go ahead and feel free to unmute if you have a quick question. All right, not hearing or seeing anything.
Well, feel free to send me questions if you have any. Reach out to me if you have any questions about this application.
Chayton did ask, were the fundamental diagrams for Aimson or Dynamic?
The fundamentals, you mean these? I'm not quite sure what he meant by fundamental. So the everything we've shown here was in Dynamic. If it was model related, it was Dynamic. At least on this, but we haven't done an application with Aimson. We've done applications with Dynasty, DTA Lite, Dynamic, of course, and I know that Chayton has actually done some applications using the Zoom and some of the built-in DTA packages there. Oh, okay. The shape of the speed flow, yeah. So this actually, I actually have a spreadsheet. So that's a Peter Bosa's spreadsheet that produced this. Yeah, this is great. I love these. The spreadsheet is excellent because what it allows us to do is look at, if I go section by section, station by station, and create these models, I've found that the flow rates rarely approach 2,000 vehicles per hour per lane. And that is actually the standard flow rate that we use or capacity that we use in our models is 2,000 vehicles per hour per lane, like on our freeways. And after having created these plots for enough portal stations, I think it's safe to say that it's rare that you see that type of flow rate in our region. And it's led us to maybe reconsider some of the maximum flow rates that we would use, not only in a DTA, but also in like our static assignments. And I have a spreadsheet that does this stuff. That's a presentation on its own, but it's a very useful tool.
Yeah, I think that's really important, Peter, and it really goes to stress how important local calibration is for these models. Because we have data down in California that some of those freeways are pushing 2,200 plus vehicles per hour per lane. So yeah, we're certainly not getting that capacity here in the Portland metro region.
Randy, do you think that's like a geometry issue, a facility issue, or is that more like a driver behavior issue?
Oh, I think it's a combination of both. Having driven down there, there's definitely a little more aggression in the driving population than up here.
They're not Oregon nice like this, right?
Right.
I should just label this Oregon nice.
There you go.
Lots of space between vehicles.
Okay, well, thank you, Peter. We're gonna go ahead and jump to our next presenter here. So David Hensel with RSG is going to be presenting on an example DTA application from Michigan. using DTA for Ford Motors Corktown demand responsive transit simulation. And David is in his third year with RSG as a transportation modeling analyst. His primary focus is on travel demand forecasting and has contributed to the development of many travel demand models, including the Detroit, San Francisco Bay Area, and San Diego. He's also an active software developer on the Activity Sim activity-based modeling platform, and he comes to us with a background in physics. So David, I'll go ahead and let you take it from here.
Thanks, Randy. So you guys should all be able to see my screen. I guess holler at me if you don't see it. But we're talking today about our work with Ford Motors on a demand responsive transit simulation in Wayne County, Michigan, which is the county that surrounds Detroit. So kind of where we're going here, we use MatSim to simulate traffic in the greater Detroit area. So I'll walk us through some background, a little bit on the MatSim tool in general, what we did to develop the network and put some demand on there, and then the modeling of this demand responsive transit, which is essentially like an Uber pool service, but with kind of an eye towards automated vehicles. So project background, it was a collaborative effort between RSG and ETH Zurich. ETH Zurich is one of the primary developers and users of MatSim, so we leaned on them a lot for MatSim specific knowledge, and then RSG was primarily responsible for a lot of the network and demand development. So the project essentially started with this new, or I guess old building in the Corktown region of Detroit, just outside of downtown Detroit. Ford Motors bought this historic building, the Central Michigan Station, a couple of years ago, and the idea was that they're going to turn this kind of decrepit old historic train station that used to be kind of the jewel of the community in this area, but that has since been run down, into a brand new office focusing on autonomous vehicles and all of Ford kind of administrative offices. So that's kind of the idea here, is that they wanted to understand what the impact of adding 5,000 workers or something like that to this area and how it would impact the traffic around the region. And not only that, but explore different and new mobility options like this Uber pooling type service, but with an eye, like I said, towards more autonomous vehicles and ride sharing options. Fun fact, this is also the building where this fight scene from Batman versus Superman happened. So if you ever watch that movie, you see them fighting in some old decrepit station, it's actually this building that Ford is currently remodeling. So I'm going to talk a little bit about MatSim, kind of what it is. It's a DTA model. MatSim stands for Multi-Agent Transport Simulation. It's an open source application written in Java, and it just simulates the flow of traffic and congestion based on the daily schedule of individual synthetic travelers, or agents in this case. MatSim, it applies an iterative co-evolutionary approach to maximize the utility of each traveler's day. So that's kind of given by this MatSim loop here, where you start with some scenario data. So each individual person's plans, the individual network links and architecture of the network. And then you kind of route each one of the agents on the network. There's a lot of parallelization and computational optimization that happens here to get everybody to go where they're going. And then there's some scoring function that determines how quickly or how well an agent goes from their origin to their destination. Generally, MatSim has the ability to change people's daily patterns to try to reach convergence with a kind of co-evolutionary approach. We didn't really want to allow people to change where they were going or when they were going there. We did allow people to change the route, how they got there, and the mode, what they used to get there. So there's kind of a scoring function, which we limited in this instance, and then there's this replanning kind of loop that comes back, and you kind of run this until you reach some convergence. And then, of course, we want to do output analysis like traffic volumes and mode choice distribution, things like that. So MatSim, it really works on a link level. So you'll have individual agents, but you don't necessarily track the vehicles individually within the link. So it's a link queuing model. So it's kind of a mesoscopic approach here. And that's just to be able to model larger regions in the computational time that's reasonable. So kind of an overflow or workflow diagram, I guess, of what kind of goes into this whole thing. And we'll kind of talk about each one of these pieces here as we go through the rest of the presentation. But you'll have a network. We got ours from OpenStreetMap. We also included some transit data in here. We used the region strip-based model as our demand, and we assigned them to the network. And then we fed MatSim in, fed this all into MatSim. And I guess when I say assign trips to network here, I mean starting and ending links on the network. And then we allowed them to be simulated by MatSim, right? And there's a mode choice model where we added this DRT option, and then we'll have some output analysis, and then this process kind of gets iterated as a function of how we're doing. So moving on to the demand and network creation. So the demand, as I just mentioned, came from the region's trip-based travel demand model, the Southeast Michigan Council of Governments, which is the MPO for this big 7-county or whatever region that they have here. There's almost 3,000 TAZs in this area, corresponding to 21 million person trips. We were really only concerned about this Wayne County modeling region here. So that essentially trimmed it down to only about 11.7 million individual MatSim agents. And we distributed them temporally and spatially from the SimCog trip-based model onto our MatSim network. I think it's important to kind of note here that we use the SimCog travel demand model because it's already a calibrated and validated model. We didn't really want to necessarily, try to create a travel demand model from scratch for this whole project. So the idea is to use something that's already been created and used and validated. And the idea is also that it could be a little bit more easily replicable to other regions that have similar trip-based models. So the network, OpenStreetMap, if you haven't heard of it, is just an online database that contains all the streets. So there's a open source Python package called OSMNX that we use to extract the network. And you can see, right, we just kind of drew this polygon and then used this Python package to extract it from the database. And we ended up with approximately 236,000 individual links here, which is a lot. So what we did was we wanted to trim the network so to help our computational time. We did want the detail in downtown around the Corktown campus, which is like kind of right here. This is downtown Detroit. The main area is here, but of course you'll have people coming, moving all over the really dense metro region here. And then what we did was we took the SimCog planning level network and we trimmed out all the kind of auxiliary streets outside of the downtown region to avoid unnecessary computation time. There's a lot in here that can be really tricky when we're talking about network cleaning. So here's an interesting case where we trimmed the network, right? This is kind of a smaller road, but these were more main arterials. And so this just happened to be kind of on the line that was cut off. But this actually created a routing problem. So even though the roads are correct here, because we trimmed this out, there's now a routing problem because this is a one-way segment and this is a one-way segment. So if you have any agents that try to start on either one of these links, when you distribute your agents onto the network, then they're not allowed, there's no way for them to route out of this segment. So it's like things like this that can be very tricky when you're dealing with a large scale region with a lot of network links. We also included some transit. So there's a Java application called PT2MatSim, which takes the GTFS data for this region and integrates it with MatSim network. So you can kind of see the coverage. Detroit doesn't have a whole lot of transit in it. There's one Q line here, which is a streetcar that kind of runs on one street in downtown. There's a central business district circulator here called the Detroit People Mover. And then there's this bus system, and then there's a few more bus routes that kind of extend out into the suburb region. So you can see this is what it kind of looks like when you load it up in MatSim. We have a really dense network in the downtown region, and then a planning level network around it. And then when we include transit, it'll include extra links in here. And so you see that, as I said, it really extends out in the suburbs, and that's what all these extra links are up here, is the bus network that extended beyond our model region. So to kind of summarize here, right, we started with OpenStreetMap for the Wayne County. We trimmed it. We added some transit to the network, and then converted it into a MatSim format. And we were able to do all of this with open source data and open source tools, which I think is pretty cool. So now we have a network and the demand on here, we can actually kind of load it up. And so I'm playing this little video showing, if I zoom in here, the individual MatSim agents that are going around on the network. And you can kind of see, if you kind of look in this region, there's a link that gets congested. And so that's like the link level queuing that I was discussing at the very start that the MatSim kind of works on. So it's pretty mesmerizing to kind of watch this for a little while. You can kind of see that there's portions around here in the network in this video that are more congested than others. And so what you can kind of do with this, if I kind of move on and take kind of snapshots throughout the day, is you can kind of see where the problem spots are on your network. So here's your volume at 8 a.m. There's a big freeway interchange right here. There's freeway coming this way and a freeway coming down. And as you kind of zoom through the day, 8 a.m. to 10 a.m., it grows. And then 1:30, it really grows. And then by the time you're in the PM peak period, it's really spread, and it doesn't get any better by the time 6 o'clock rolls around. So what this really leads us to is there's generally regions in your development cycle where you have network problems. So for example, there's this interchange right here. There's 8 Mile Road and I-75. And there's this little link, like this one right here is a link in the network. And in reality, it's 2 lanes, kind of this split lane deal, but it was coded as 1 lane from OpenStreetMap. So here's an example where people are coming off the highway or trying to get on the highway, and this one small tiny little lane backs up, which causes a backup onto the highway, and it just spreads throughout the day. So very small problems in your network can really cause headaches and when you're doing scales like this. So after we kind of sorted out a bunch of those issues, we were able to look more at the demand responsive transit portion. And the way that we incorporated this was by using a mode choice model. So we have our usual car mode, some non-motorized modes, and public transit. And then we added an additional demand responsive transit mode here. The parameters for this mode choice model came from the SimCog trip-based model. They include things like in-vehicle time, out-of-vehicle time if you're doing things like walk to transit, or walking or biking. We also have some travel costs, auto operating costs or toll costs. We have utility terms based on the household income and the availability of a vehicle for the household from which that agent comes from. And so what you essentially get is for each person, you'll have, you sum up all the utility terms, and then you create a probability from that. And then you randomly draw from that probability distribution for each person to be able to have some people that select demand responsive transit. And also some elasticities based on travel cost or whatever parameters that you have in your model, and that will change. As you change those, that'll change the probability that people will select your given mode. So the way that the demand responsive transit simulation really worked here was that an agent would go through the mode choice, they would see some travel costs, and they would pick the demand responsive transit mode, and this submits a request to what we're calling the centralized dispatching system. And then this is responsible essentially for telling which DRT vehicle is going to be able to pick up this agent, if any, right? So in some cases, there's no really available vehicle that's within range of the agent, and in which case they might get rejected. So like I say here, dispatch algorithm calculates the detour time based on the maximum detour time and the wait time. So it already knows where that vehicle is going when the request gets submitted. And then it just assigns the vehicle with the smallest detour time for pickup and drop off. So we tried a bunch of different scenarios. We tried multiple different fleets, multiple different vehicle occupancies, the size of the DRT vehicle, and two different fares, $2 and $4 fare, just a flat fare. We didn't do any distance scaling here. And we fixed sometimes here, we said that the customer was only allowed to wait 15 minutes. If they had to wait for more than 15 minutes, then their request was rejected. If there was more than a 15-minute detour time for the vehicle, then that vehicle is not allowed to pick them up or drop them off. And then there was an additional almost 2-minute wait time at each one of the stops that was included. And so as we go through our simulations, so kind of talking through these plots here, this is the number of travelers, or the number of agents, the number of people who requested rides, the number of vehicles in the fleet, and then there's two colors. The $2 fare is the blue one, and the $4 fare is the green, the gray one. The lines up here are the total requests. So for a fleet of 100 vehicles, you see, there's 35,000 requests, but only 5,000 people actually got served. So the rejection rate is extremely high. If we double the fare, then the number of requests goes way down. There's been a lot fewer people who are willing to pay $4 than $2 to take this service. But we still have a rejection rate of 1/3 or something like that. I guess 2/3 being rejected. And so you can kind of see that these go through this plot is essentially the inverse of this one. But as you get to higher fleet sizes, you have 1,000 vehicles, you're still not really able to serve all the rides. So a large portion of rides were rejected. That's kind of a function of the size of the area that we were working with, right? Wayne County and Detroit is pretty large. And so there's a lot of area to cover. And so even with a large fleet size, 1,000 vehicles, we're still rejecting people, and we're still having vehicles that are not being used all the time, right? Because they just don't have somebody within 15 minutes that they can pick up or drop off. And also as a function of this low density in the Wayne County region is that the occupancy for these vehicle rides was pretty low. So you can see the amount of deadheading of these vehicles here. And most of the passenger distance is with one passenger in the vehicle, and very small amount of ride sharing with two, or 4 is pretty much non-existent. There's a couple cases where we have a couple vehicles that had up to 3 people in them. We also took a look at wait time. So the average wait time of the fleet. It's not very sensitive to fare. It is, of course, sensitive to the size of the fleet, as you would imagine. As the size of the fleet goes down, the wait time goes up because the density of vehicles on the network that can pick and drop you off decreases. So to kind of summarize here, most of the DR trips ridership comes from the car mode share. So that's where we saw a huge shift, was people switching from car to this DRT mode. That's probably not surprising, considering most of the people that are in the Detroit region use car anyways. It's a very low transit share area. The county's relatively low density leads to a very low potential for ride sharing. You could think of scenarios where you would restrict this service maybe to just the downtown region, in which case you might see a better vehicle utilization. The fleet might be a little more active, but then you're of course decreasing the size of the share of people that could possibly use the service. We found that increasing the fare from $2 to $4 was very sensitive for the number of people that were riding. It was almost 1-to-1, so a decrease in fare by a factor of 2 essentially took away half of the riders. We worked on the average wait time, how that's affected by fleet size. Network congestion is also an issue here, of course, as is like the number of rejections. As you have a lot of network congestion, right? If our DTA model is not very well calibrated, or if we have errors in there that's leading to congestion based on network problems, it kind of throws off a lot of this stuff. Some limitations and kind of some future direction is there's a lot of parameters to play around in this space, especially with the DRT service and mode choice and kind of the assumptions that might go in there. It would be really cool to use the demand from a tour-based instead of a trip-based model, and be able to kind of feed this back into a regional travel model to have, you know, more accurate changes based on the mode shares that we were seeing. Run times for this model were very long. It took multiple days for us to do that MatSim loop iteration and converge to a solution. And some other, I guess, some general takeaways I have on here. As you kind of saw, and the point I tried to make here was that network accuracy is very important for DTA. But DTA also provides really the unique ability for us to visually see the routing and spacing, especially of a shared fleet like this, where static assignment doesn't really do, you know, routing of vehicles on the network. So if you want to understand what your fleet is doing at any given time, you kind of need a tool that does that. All of this can be seen in a TRB paper that we wrote as part of this work, if you're interested. So I think I'm like right on time. That was my last slide. Any other questions for me?
Yeah, perfect, David. Thanks for helping us keep on time here. So yeah, there are a handful of questions in the chat. I don't know if you want to
Let's see.
dig up those yourself, or if you want, I could read them for you.
Yeah, I can't. All right. Can't find the chat box button, so maybe if you can. just read
Okay,
them for
sure.
me.
So Alex Benardi is asking the first question here with, does MatSim provide a way to calculate an optimum size fleet for the demand?
Not really out of the box. You might be able to like cheese it somehow. I guess my answer here is no, but you could maybe do it with some really clever thinking.
Yeah, that would certainly be a pretty helpful tool to have. Okay, next question up is from Chayton. Is the dispatching algorithm part of MatSim or external tool? Any more details available on that?
It's an extension of MatSim, I guess is the best way to put it. So MatSim, you can go find it's an open source tool as well. So you can go look at the repository that they have. I don't think it's part of the official release. It might have been pulled in recently. Part of this demand responsive transit, I think was, an extension, but I think the work was being done to pull it in, and it might be in there right now, more integrated.
Gotcha. And Alex has another good question here. Is deadheaded included in the congestion calculation? Are those vehicle trips in the assignment?
Yeah, yes. So you saw, right, this, these distances for deadheading, MatSim output actually includes like full vehicle routes. And so you can kind of extract exactly where each individual vehicle goes on the network. And from that, you can calculate distances on an individual vehicle level. So that's how these plots were created. We essentially grabbed those vehicles on the network that were doing this DTA, and we just calculated from their whole day and what the vehicle occupancy was to calculate deadheading. And also because in the simulation, they're included in there, so they also contribute to congestion. But the number of vehicles is pretty small, so it's not like they had a major impact.
Gotcha. All right. And another one in here from Alex. I probably missed a slide, but how much variation was tested in paying for the ride versus the cost of ownership / operation?
Paying for a ride, meaning on the DTA versus the cost of owning a vehicle, or the cost of operating the vehicle itself?
Yeah, sorry, I wasn't sure how to type that question quickly. Basically, was there variation in how attractive it was to take this mode versus owning your car? Like, how much sensitivity was testing around? Well, like if it's free, I'm gonna that's clear. I don't know.
Yeah, so that was kind of the point that I was making about it'd be cool to integrate this with the regional travel demand model. If this becomes a mode and there's more available and people are willing to take it, does that mean that less people are going to own cars? That's not something that was explored as part of this project, if that's answers your question.
Sure, but was the demand, that makes sense. So the ownership is somewhat static, but was the amount of shifting to this new mode function of, was there a variable tested in how much the ride costs the chooser?
Yeah, right. So that's this fare cost here. And so if you look at the mode choice model, this travel cost, the fare would come into this travel cost if you're in the demand responsive transit portion, right? Or if you're in public transit, it'd be the fare of the transit vehicle. Or if you're in a car, we have some auto operating cost parameter that comes in there as well.
Got it. Thanks. I just missed the slide. Thanks so much.
Okay, and then final question here before we jump to the next presentation from Peter Bosa. Did you validate the MatSim all-day network results with observable data?
Yeah, so we took the counts that were from the SimCog model, or is it the SimCog region, and we linked them onto the network, and we did some count analysis as a function of time of day. That was kind of the main validation plots that we used, and we also wanted to make sure that the mode choice model was validated as well based on the mode shares in the SimCap region. And in
And
the model.
just a quick follow-up, David. Thank you for answering that. Did you have to do some sort of like demand adjustment for MatSim? I mean, or did you find that putting in the raw demand from the SimCog model, you were able to match, you validate pretty well against the counts?
Yeah, I mean, that's a great question. I think the counts themselves, matching the counts was more about the level of congestion, which had more to do with the network cleaning. In terms of the demand, I don't think I have a slide in here talking about the demand a whole lot, but this was tricky because, right, the trip-based model has very defined time of day periods. And if we want to be completely consistent with the trip-based model, which we did, I mean, we wanted to kind of stay with that. There's these discontinuities that happen at these time of day periods where, like from the midday period to the PM peak period, for example, you have kind of this spike in demand. And even if we kind of distribute people in a way that makes sense temporally on the network, you still have this kind of discontinuity because there's a whole lot more people that kind of show up on the network at 4 p.m. So that was a challenge for us, and it wasn't necessarily really resolved. So if you were to look at individual like half-hour time periods on the network, the validation might not look as great as if you were to look kind of at the whole day.
Okay, perfect. Well, thanks again. We're gonna go ahead and jump on to the next presentation, which myself and my colleague Kayla Fluskies will be taking the reins here. So let me share my screen. Okay, so our presentation is going to be on the macro side of meso modeling, an ICA-based assignment case study in Hillsboro, Oregon. And if you missed my intro from Garth at the very beginning, I'm Randy Johnson, I'm Senior Transportation Engineer at DKS. I lead our multi-resolution modeling discipline group. I'm also co-chair for the local ITE, Oregon ITE SimCap Group, which is sort of co-sponsoring this event. Feel free to reach out to me if you have any questions about SimCap and want to learn more about the events we have coming up. And then I'm also a member of the TRB Simulation Committee. And then I'll be kicking off this presentation with a little bit of background of the model development in Hillsboro and really what this sort of set of tools is. And then Kayla will be presenting on sort of the actual project applications. And Kayla is a transportation engineer with DKS in our Portland office. She pretty much does the full gamut of multi-resolution modeling from macro, meso, and micro, and really likes working on projects with a focus on multimodal solutions. All right, if I can get my slide to advance here. So multi-resolution modeling, where does DTA fit in? So Peter and David kind of talked specifically about the DTA applications. Peter provided a little bit of an overview of sort of the macro, meso, micro. And the important thing here is choosing the right tools for the project application. And that also means that you get the right data to support those tools. And with increasingly constraints on funding, policy changing, we're having to be more creative in the solutions we develop, and we need to have strong data to support those. And so how do we manage our systems when we have limited funding, limited right of way? And we want to make sure that we're doing the best investment of those dollars that we can. So we want to make sure that we're choosing the right tools. That's an important aspect here. I'm not going to go too much into the multi-res overview. Peter did a pretty good job in the first presentation, but there are many tools with many different needs, different software packages for each of these scales. And so it's important to know what are the benefits, the pros and cons, limitations of each of these software packages, and maybe what combination of tools you'd want to include. So again, recap, the macro side, generally referred to as the regional travel demand model. It definitely is at that regional scale and influence. Applications, congestion pricing, route diversion, parking cost, mode shift, transit capacity, demand development. There's a whole range of different applications. But as Peter mentioned, one of the key things is it's not necessarily capacity constrained in the way that a mesoscopic model is. Mesoscopic can be kind of fairly large sub area. It's still challenging to do a full regional scale, but there are a few applications where that is being done. And small to medium sub areas are quite common applications. But now we're getting closer to the simulation. So we're actually we could adjust some driver behavior and having detailed junction control, dynamic traffic assignment over more discrete time periods. And so this, now that we are actually capacity constrained, we get a little bit more effective evaluation on something like route diversion. The dynamic examples that were presented, that's a lane-based DTA, but products like Dynasty, there are link-based DTA, so a little slightly simplified version of DTA. And all these are great applications for queue spillback between intersections, understanding the impacts of peak spreading or how a project may reduce the hours of congestion. And ultimately, you're going to have the benefit of faster runtime over micro simulation. So really, the concept of multi-resolution modeling here is a combination of these tools. There's a whole variety of different approaches that you can go. You know, if you're doing a detailed operations analysis, a corridor study, you might go straight from that macro to the micro with some post-processing for the volume development. That's a very traditional approach. With the Hillsborough example that we're going to present, we're inserting a meso step there in the middle to introduce more refined assignment, more detailed loading of the network. And you could even go just straightly from macro to meso. That's more the application that Metro is doing with the congestion pricing. And then we don't see it too much yet, but doing the full macro, meso, micro, but getting that feedback loop back up the resolution, whether it's into a meso model or all the way back into the demand model. So there's a variety of different combinations that you can do, understanding these limitations, benefits of the different tools, and choosing the one that best fits your particular project application. So in that meso world, there's more than just dynamic traffic assignment. The ODOT APM has a chapter on mesoscopic modeling, which is really more focused on a windowed approach. It's more of a detailed sub-area analysis. And so with that, you basically enhance the network. You're cutting out a sub-area, so you have a fixed cordon boundary, so that demand going in and out remains sort of fixed. Generally, a lot of the regional demand models are pretty coarse in their network. And so this process generally involves adding some additional network connectivity. Sometimes it means disaggregating zones. Other times you're just simply refining the connector loading and maybe even the shares of those connectors in terms of getting the right demand to the right locations to the network. That's important when you're going to be ultimately focused on more an operations-based model. And then for our next steps and applications, we're really, again, focusing on operations. So we're adding in additional network detail. We're coding, similar to what you would do in a dynamic model, we're coding the individual lanes, but we're also, I guess, in addition, coding in the signal timing as well. So that's going to allow us to do two things here. One, we have all the inputs for geometry, signal timing, volume. Now we could basically do HCM analysis on the fly. So that'll allow us to get our level of service, volume to capacity ratios. And so as we run through our projects, run different scenarios, alternatives, we could see the immediate results without having to then export, go into a tool like Synchro or HCS and process the information externally. So it's all sort of integrated. The benefit is we're actually using that HCM calculation as part of our volume delay function or impedance model in the assignment itself. So the assignment is responsive to if we add additional lane or we change the control type from an always stop to a signal, that delay is going to go down and it'll pull more demand in there. So while not a true dynamic assignment model, you're going to get a more refined assignment based on the operation characteristics of the network. And so that's the process that we applied here in Hillsborough. Hillsborough is actually a pretty early adopter in this. let's see, I've been with DCAS for coming up on 9 years, and I was with PTB for about another 9 years before that. And so we started on the downtown Hillsborough modeling probably 2005, 2006. And we've used this same set of models kind of refined over time, but we've used it for about a half dozen projects in the downtown area, from looking at street vacations to conversions from one-way to two-way streets, some regional impacts. And then we have 2 projects going on right now that Kayla will be covering in detail, looking at adding a couplet, as well as sort of refining and modernizing an existing couplet to add more multimodal facilities, improve pedestrian connectivity. But you can see here, this is what the regional model, how it's reflected in the downtown Hillsborough area. We've gone through, we've added in more local connectivity. We disaggregated the zones down to the block level. That allowed the city to go through and do some sensitivity testing in terms of different development scenarios, and basically create a build out scenario. And then other unique characteristics we have within Hillsborough is we have some major regional through routes. We have a grid network. We also have light rail that comes through with frequent preemptions. And we have queue spillback between multiple intersections with short blocks. So traffic is very dynamic in how it reacts to congestion. And you can easily kind of go around the block to get around a temporary queue buildup from a rail preemption, or to kind of stair step through the network to get around that several block queue from a traffic signal. Early on when we developed this, we actually used dynamic traffic assignment at the micro simulation level. That was cost benefit really didn't pan out. It was very tedious to kind of calibrate that with such a tight grid network, and using 15-minute time intervals. In reality, the decisions of routing changes were done at a finer time increment than 15 minutes. So in our current iteration, we're basically pulling the refined routing from the meso model, putting that into the microsimulation model. And then we've developed sort of localized dynamic routes. So they're sort of key diversion routes where if a particular corridor will build up, then you're going to get a certain percentage of traffic that's going to take this secondary route. So we have this sort of fixed dynamic route logic set up directly in the microsimulation model piece. So that's sort of the general process. I'll go ahead and kick it over to Kayla to talk through our applications.
Yeah, so just a little bit of context for those who might not be quite as familiar with Hillsborough. I've got this little cloud around the downtown area, and then the orange lines represent OR 8, which serves a lot of regional traffic kind of between Beaverton, Hillsborough, and then out towards Forest Grove and Cornelius on the west side. And then you also have that yellow stretch of 10th Avenue, kind of north of that OR 8 section, that also serves a big chunk of Hillsborough, sends you out towards the Intel campuses and the airport, and also out towards US 26. So within the downtown area, there's a lot of regional trips going through the downtown. So there's kind of 2 key drivers for the projects that we're working on right now. Randy mentioned we're working on 2 kind of separate projects, but for simplicity's sake, I'm going to kind of lump them into one here. So 2 of the key drivers for these projects are really, economic revitalization and re-envisioning of that 10th Avenue corridor, both the OR 8 stretch and the 10th Avenue stretch to the north. And then also improving efficiency and safety for kind of all modes of travel. We'll move to the next slide, Randy. Here's just a couple quick images to give you a sense of what 10th Avenue and Oak/Baseline or OR 8 look like today. So Oak and Baseline are both 3 lanes in each direction. There's pretty limited parking on Oak Street and limited pedestrian crossing opportunities with no bike facilities. If you look at 10th Avenue, it's a 5-lane corridor today. There's a lot of development that's really curb tight, no bike lanes, narrow sidewalks through a lot of 10th Avenue. And the City of Hillsborough's TSP currently identifies a project to widen 10th Avenue from 5 lanes to 7 lanes to address capacity concerns. And so that would obviously have a pretty big impact on kind of the form and function of this facility and impact on adjacent businesses. So as part of this project, we're really looking at maybe alternatives to going from that 5 to 7 lane corridor. So some of the key objectives that we were really trying to understand and why we wanted to use this multi-resolution approach is that we're really trying to understand kind of the regional routing aspect of it, right? So if we have all these regional trips going through downtown Hillsborough, are there opportunities to have those regional trips off of the downtown facilities? We also were looking at changes to local circulation patterns. So understanding that the city's grid today is a one-way network when you get towards Fifth Avenue in downtown. And so if there's any changes to local circulation patterns, if that can reduce your out of direction travel, improve connectivity for bikes, what impact would that have on traffic operations? As Randy pointed out, the meso model, the way we coded it, did allow us to look at that intersection operation level detail, so HCM operations, and then really understanding how we could test changes to the roadway configuration to try to see if there were alternatives to that 7-lane widening. Next slide, Randy. So at the macro level, really looking at that, trying to answer that regional routing question, we tested a couple different routes shown in the blue lines here on the screen. We were kind of throwing feasibility out of the window just to see, is there even potential to drive trips to some of these other facilities and get them off of those downtown facilities on OR 8. And really there wasn't a high driver to get vehicles off of OR 8. And so taking into account the limited feasibility of these routes, the cost really would not pan out. Go to the next slide, Randy. We then kind of bumped it down a level to help answer the local circulation question. So using the meso model, we were trying to understand if you could convert either a subset of the city's one-way streets, shown in the purple there, or all of the one-way streets to two-way downtown. Again, trying to reduce some of that out direction travel, give you maybe better opportunities for some bicycle connectivity through here as well. And that was a great candidate for that meso model where we had more of that refined local street network. We had that block by block zone disaggregation to really understand the circulation changes with this type of project. Again, the other application for the meso model was really looking at intersection operations. So we were able to forecast the future traffic volumes using that disaggregated zone structure again, and analyze our HCM6 operations. Like Randy mentioned, you can really do that on the fly as well. So as you're testing changes, you can very quickly see the impacts rather than having to bring it into a different software platform. And this also was what we used to get that routing into the micro simulation model, like Randy mentioned. So then finally, I've got a video here on the screen that just is a really quick video we put together to show the micro simulation side of things. And so like Randy mentioned, we wanted to really understand the impact of few spillbacks between intersections in this congested model, understand the impacts of the light rail crossings, and then still have the flexibility to do some localized dynamic routing here without going to the time and effort of getting the truly dynamic assignment. And that, again, that localized routing did allow us to have kind of that finer level of time intervals, like Randy mentioned. And so, the exciting thing, like Randy pointed out, putting development cost into tools like this, he's been working with these models for quite a while now, since 2005, 2006. And we still have additional applications that we'll be using these models for. So one of the outcomes of this project is going to be looking at selecting a locally preferred alternative and ideally a TSP amendment so that we can look at more recommend more unique concepts. Like this is a couplet concept here for 9th and 10th Avenue that's being shown on the screen, to amend the TSP and not have that 5 to 7 lane widening impact. And then this model will also be used in part for some analysis that we're doing on TV highway, looking at BRT operations. And so those are kind of some next steps for these models in this process. If you want to switch to the final slide, Brandy, I'll pass it back to you quickly.
Awesome, thank you. Yeah, and just to point out on this example, all that blue is sort of basically area that can be reclaimed for future placemaking. And so, what was in a older transportation plan of going from an existing 5-6 lane to a 7+ lane facility and wiping out a lot of right of way and existing businesses, where a lot of communities are kind of going away from couplets. This particular case, given the unique sort of funnel of regional traffic through the downtown, this is actually allows the city to create a better place along 10th Avenue, going instead down to 2 to 3 lanes, adding on-street parking, bike facilities, and some additional amenities. And so really demonstrating that through the operations and the modeling process here. So just kind of a quick overview of the benefits of the multi-resolution process. It's efficient and more realistic on the demand development side. Typically with you're taking future demand out of a travel demand model. There's a lot of post-processing that you need to do to really get it to that project level. And here we're kind of effectively doing that directly within that meso step. The ICA-based assignment provides more realistic routes than macro model with lower level of calibration needed than DTA typically. And so there's a lot of benefit that you could do just simply from that, like the title of the presentation stated, the macro side of meso. And this even supports integration with DTA tools. So you could certainly swap Dynamic in there if you're using a different software package across the different resolutions. And the meso to micro also saves some time on the network development if you're doing the export from the meso to the micro. And a big thing here is one meso model can support multiple projects. So it's not a one and done. Like I said, we've used this for over 6 projects over a span of 15 years. And, we've got to do some updating here and there, but there's been a lot of economies of scale and savings there. And then ultimately it's a cost-effective solution for realistic and confident results. And you have not only the data to back it up, but, modeling results that stakeholders, especially non-technical stakeholders, can see. So with that, we'll go ahead and close our presentation. Any questions?
Randy, this is Peter. I have a quick question.
Yeah.
For you or Kayla. How much difference did you find the signal timing plans make at the meso scale in your model? Are they as impactful in the meso model as they are in the micro simulation? Are they less impactful? Did you find that if you didn't have the actual timing plans in place, did you get markedly different model results in your meso model?
I would say it really depends on the details of the specific network. And so like in one case on Lincoln, which is just north of the downtown area, where that ties into Cornell, the route Kayla showed going up to towards Intel and sort of North Hillsboro. When we went from an unsignalized two-way stop controlled to a signalized intersection there, that actually pulled quite a bit of traffic, just because the alternate routes that are being used before were fairly congested. So again, it depends on the network specifics, but it can make a pretty substantial difference.
And similarly, because of the grid structure through downtown, there were definitely a couple locations where some minor tweaks in intersection signal timing would impact some of the routing choices with the ICA assignment.
Is that trying to like get coordination correct so that, or is it more like I'm just trying to figure out, because from my experience, at least at larger levels, the timing plans have an impact at the individual intersections, but the overall routing, unless like the timing plan is really egregious and causing a lot of backup for a particular movement, I've found that like generic timing plans are a good first substitution, maybe for, if you don't have the capability to maybe get all the timing plan information right away. So I was just curious what your experience was. If you found that using a generic plan would be okay, or it looks like you had very detailed information for each of the locations, and you were actually able to utilize that information.
Yeah, I'd say because the scale of like the DTA projects you're working on are considerably bigger, and I think that more generalized timing plans work well when you're the type of output that you're trying to get. When we're trying to look at specific queue lengths, do we need to add a turn lane? Do we meet the regional mobility targets on VC thresholds? And the scale of the model we have, then at that point, really, we do need to go down to, we have to have the real timing in there, as if you were doing a synchro analysis. And then ultimately, we need that same level of timing for the vSim model as well. So, and we're effectively using the same controller between the meso and the micro.
Randy, we're at time, but there is a question in the chat from Jin Ren. Do you want to take that quickly and then we can move on?
My chat is not showing up. So if you could read that to me, I'm happy to answer it.
Jin's question is ICA an intersection delay based assignment approach, or how does the meso model take care of link delays?
Sure. So ICA, intersection capacity analysis, instead of using a traditional volume delay function, your impedance essentially comes from the delay results from that intersection capacity analysis. And so we ran ours using HCM6 methodology, but you can certainly run other methodologies as well. Okay. Well, let's go ahead and move on to our next presenter here. Get my screens organized. So up next, we have Chetan Joshi with PTV. He'll be presenting on calibration of meso and simplified car following models. Chetan's a principal engineer with the PTV group. He is involved in providing travel demand modeling and simulation services to clients in North America and select projects worldwide. He also works on prototyping and testing of features in both vZoom and vSim. So take it away, Chetan.
Yeah, thanks, Randy. Can you hear me?
Yep, loud and clear.
All right, great. So we've seen some cool project applications earlier, and this one probably will be quicker, but we thought we always asked about questions related to methodical calibration of car following parameters and such. So thought we'd do something in that direction and share some results. So we talk about simplified car following models in this presentation. Here, the background for car following. We have car following model generally described as an approach to model traffic behavior. In the context of traffic simulation, it's used to capture the interaction between a driver and car with the surrounding traffic. And then the motion of vehicle is generally modeled as sort of control systems approach, where there's feedback between the lead vehicle and the following vehicle and constant correction for some sort of speed differential. In traffic stream flows, there are typically two types of traffic stream flow models. One is a single regime model. So in this kind of model, same model is used for congested and uncongested flow regimes. And this is more typical of earlier generations of models. Some of the more known models for single regime case are Greenshield's model, Greenberg model, modeled by Drew and Eddy, and so forth. Multi-regime models are different in that there is a certain critical capacity or saturation rate, and based on certain internal rules, it's typically modeling the flow in two regimes. One is the free regime, where there is no congestion. So it's essentially the free flow regime. And then there is a congested regime where a different following model is applied for the following regime. It was developed to overcome some limitations of the single regime models. Examples of the multi-regime models include the Wiedemann 99 and 74 models used in VISIM, Gibbs model, which you might see in IMSUN and such, and then Pipes model, which is more generally kind of the linear or simplified model, which you might see in Core Sim, Free Sim, and so forth. So in VISUM SBA or VISUM simulation-based dynamic assignment, we have implemented a simplified car following model or linear model, which is kind of like a Pipes model like car following model. Over here, one of our objectives then was to calibrate the simplified car following model methodically and with data sources that are more generally available. For example, ATR like loop detector dumps and so forth, and use that macroscopic data to derive some of microscopic parameters required for the car following or simplified car following model. And then see if the procedure can be standardized. That's also kind of transferable because sometimes data is not that cleanly available. Loop detectors can be broken sometimes and not easily accessible and such. So Oregon, for example, has all of these different station locations, but we were not quite able to extract the detail, speed density. But it seemed like Peter got some luck with the portal data. So that would basically be the type of data that you would look for calibrating these car following models to get the speed density relationship and such. So the general methodology or background on this is that simplified linear car following model in VISUM SBA is kind of based on pipes like car following model form, which basically means that the fundamental diagrams would look like this. So it's a triangular fundamental diagram for flow density. And you can see that there's a branch over here, which is the lower branch of the model with speed flow, which is the congested regime, and the flat branch is the uncongested regime. So those are the two regimes of flow in this particular model. The mathematical form of this is essentially given like this, where headway has a linear relationship with a certain model parameter and the speed. So converting that with Q is equal to KU, the basic equation of flow, you get this kind of relationship. Over here, you basically have headway, density, HJ is the jam density, Q is the flow, U is the speed, and C over here is a certain driver sensitivity parameter. And this is what we try to calibrate or tune for calibrating this car following model, which yields that capacity or headway that gives you the simulated capacity in that dynamic assignment. Now, with this pipes model formulation, we have this property where the model basically has these kind of boundary conditions. So in the congested regime, your Q critical is like Q max. So if we just solve for these boundary conditions in the prior form, we can directly get that driver sensitivity parameter C as this C is equal to 1 divided by QC, which in this case is kind of converges with Q max, and then the jam density and free flow speed. So this converting this C into seconds yields for us the reaction time directly, which is an input into the car following parameter. So tau gives you just basically multiplier into 3600, and that gives you the reaction time input at the network level. So this would be entered, let's say if you're doing this in vSOM, you'd enter this reaction time for a network level, and then you can further add a multiplier for specific links in the network if there are specific behaviors or calibrated behaviors observed over there. So then the model calibration essentially requires 3 items. One is the free speed, one is the jam density, and then the capacity. And these are readily available, generally speaking, from your loop detector dump. So these can be utilized then for calculating the reaction time, which goes into the car following model. So here we had to create this application example. So here on US 26 Sunset, we have a nice corridor with different features or bottlenecks that can be used to test this car following model and its parameters and such. We created a small network over here for the dynamic assignment. And then over here, we have a set of general freeway links in the corridor. And then there's that Vista Ridge Tunnel bottleneck. So you're going to capture 2 types of behavior here. One is the general following behavior on the usual urban freeway type links. And then what happens upstream of that Vista Ridge Tunnel, which might be perceived as a certain bottleneck with that other complex geometry that's further downstream of it. So I explored the state of Oregon ATR data, didn't have much luck in getting a detailed loop detector dump over there. And this was just on public domain, so maybe that data is available if we put in a request at ODOT. But then we also looked at some transferability or how that would perform. So then we had some loop detector dumps from I-4 Orlando, which is kind of an example of an urban freeway. And then the Holland Tunnel, which connects Lower Manhattan and Jersey City. And that would be kind of like that tunnel type of bottleneck. And the shape of that data looked like this. So on top, you can see the I-4 urban freeway shape, and then the Holland Tunnel, a little more sparse, but still somewhat useful for calibrating the model. Now here, based on the prior equation that we had listed, the urban freeway links got a reaction time of 1.47 seconds, and then tunnel links came to 2.57 seconds. And we entered this into the vSOM SBA and looked at how the queuing could be simulated on the Sunset eastbound. There was also a parameter for look-ahead distance here, which was essentially for lane orientation, where you can say that the major branches of traffic are going north and south, and the middle lane on Sunset ends up remaining free. So to orient drivers towards one lane or the other, it's possible to then also put lane changing look-ahead distance, which I won't discuss that much in detail over here, but I just placed that where that line marking or lane marking on US 26 kind of restricts the lane changing and such. But that is a separate topic for lane changing behavior, so not discussing that over here much. So with basic parameters, which were essentially like the default, which is 1.2 second reaction time, simulated the traffic here, and you can see not a huge amount of congestion seen. Traffic flows fairly smoothly here, and you can see some ripples in that pink in the corner over there, but then not a huge amount of delay is seen in this network. And we will look at some travel time segments and come to that a little bit later in this presentation. But you can see it's kind of that bottleneck is represented, but it's not causing a huge problem because it's all on the default reaction time, which gives it plenty of capacity to pass through. So next we plug in just the urban freeway parameters, which is the 1.47 reaction time, and simulate that. And over here, then you can immediately see in that corner, again, near the Vista Ridge Tunnel, that there are more shock waves going back in the pink, and it travels further back as we look at it. Over here, you can see that shock wave is a lot more pronounced in this case. And you can see that visually traveling back with the updated car following parameters for that reaction time. So it gives you an idea of how the shock wave flows back just with the change of one parameter over here. And you can see that propagating all the way back into traffic. Gives you an idea of where the bottleneck starts and how those bottlenecks propagate backwards. Then in the third case, basically we added the Vista Ridge Tunnel bottleneck function in there along with the urban freeway. And now you can see that a lot of the flow then just gets metered going into that Vista Ridge bottleneck. And you can see that the pink congestion portion starts at a different point, where if you have driven that segment, you may have noticed that you drive through some congestion, and once you get near the tunnel, you kind of get into a metered stream, which gets you through into your merge sections relatively without that much stop and go. Depends on the day, but generally. But a lot of the bottleneck over here, you can see that the shock wave propagates a lot further back, and the impact of that shock wave can be seen stretching much further back. So this kind of gave reasonable visual confirmation that it's probably not that great to use just the default. So you want to use some level of local calibration, as Randy had mentioned earlier as well. And then we take a look at travel time segments and such, and how those compare with these different parameters. One thing to mention over here, there are some routing artifacts over here that occur on that section of Sunset, where some travelers choose to take a small alternative detour to get back onto their I-405 South section and such. So here, this would be the usual route that one would take in free traffic. But in the congested stream, then we saw this with both the updated just urban freeway as well as the urban freeway plus tunnel bottleneck parameters, that this other route starts getting captured. So this kind of gives you that little variation of routing that can occur. Of course, the proportionality is still largely on the primary route, but that other route becomes attractive when conditions are more saturated, and in cases where vehicles are not able to merge into that correct lane. So they take a detour and get back on track over there. Now, to validate some of the travel time segments, again, I checked the information on 511 trip check segments. Couldn't quite extract data from it, so probably just something that I don't know how to do with the 511 website. Need better understanding of it. But then we have always the Google routing, and nowadays you can give a departure time setting in Google and get sort of an expected range of travel times that you might obtain if you depart at a certain timestamp. So we were looking at this evening peak 5:45 p.m. departure, let's say, and then comparing that travel time segment with what we got in the Visum SBA with default parameters, with a parameter, and then 2 parameters with the tunnel as well. We looked at 3 segments here, one going straight into Market Street, one going north, and one going south, and this is the general range of travel time obtained. So how does this compare with what we got through the model? This is the kind of result here. So the Market Street, you can see with default, basically it just gives you a free flow travel time on the congested segment. So not much is captured with the default parameters if the simulation is done as is. With adding the urban freeway, now you can see a little bit more congestion and the travel time comes at least within the range. And then with the additional tunnel bottleneck modeled, travel time is further congested. And this general trend can be seen on all of the three segments that we look at over here. So definitely over here, what our conclusion came from that is that it is better to evaluate and consider car following parameters instead of using simply defaults where there is some data available that will give you more realistic representation of congestion and to be able to model bottlenecks a little more accurately in terms of where they originate instead of tweaking individual intersection capacities and such. And functional and available loop detector data, ATR data, can provide quite useful information for model calibration for these driving behavior parameters. On the ability to transfer coefficients of parameters, this was just one case, and kind of because we had travel time more in ranges, it was hard to conclude anything from that observation. So some more use cases and examples will need to be evaluated before we can say anything definitive about the transferability of those parameters. And that is it for me.
Awesome. Well, thank you, Chaitin. Let's see. Any last minute questions for Chaitin? Not seeing anything in the chat here. Or any other questions for any of our other presenters? Okay. Well, thanks again, Chaitin, and thanks to
Randy, there was a question in the chat saying, how do you think the grade impacted the results?
Oh,
yeah, that's a good question. So here, in this case, we have a simplified car following model. So we don't take into consideration that aspect of vehicle dynamics. But I know what you're talking about when we are looking at sunset, that there is a grade over there, and that for sure will have some impact on the braking behavior and such.
Excellent. The other thing, Chaitin, did you play around at all with truck percentages and how that might influence results?
Yes, that's right. And I did add in over here the fleet, basically what we used was actually a network that we got from Peter. And he had classified heavy and medium trucks in there. So they had those in PCEs in there, but then I reconverted those and used the Oregon State guide for these truck types and such, and assumed a truck type over there. Of course, it's not possible to get that classified data for the truck. So car following specifically didn't necessarily apply to one class or the other, but I did enter the truck types in there.
Okay.
And that seems to have made some difference in that queuing based on when I did it without or with.
Okay, great. Then another comment came in from Mahmoud. I think it is helpful if the calibration process is documented in Zoom examples so that everyone can take the same approach. I don't know.
Yeah, sure. That's a helpful link, and I will convey that to our product management.
Excellent. Well, we're a little bit ahead of time, so we can give you a few minutes before lunch here. On behalf of Oregon ITE, I want to thank OMUG for allowing us to partner up on this topic. Garth, I'll kick it over to you for final statements.
Terrific. Thank you very much, Randy. And thanks to all the panelists today. We had lots of great content. I saw we hit 50 attendees at one point, so that was great. A quick reminder on upcoming events. We have a couple upcoming sessions later this year for OMUG. We're going to be talking about transportation network companies, or TNCs, and first and last mile transit later in the fall. And then later in the year, we'll be having a session on mobility policies, evolving best practices, moving away from level of service. And then a reminder of a few upcoming conferences for the summer through the fall. There will be a few different TRB conferences that are being offered in various places around the country. And Carol, if you want to go to the next slide. And then lastly, as many of you know, Brian Dunn is retiring, and we wanted to acknowledge his contributions to modeling and analysis statewide. And I actually noted Brian had popped in earlier briefly. So as many of you know, for those that don't, Brian has been the manager of TPOW, and he's retiring at the end of May, which is coming up very quickly here. He's been at ODOT for about 30 years, and he's been a longstanding champion of OMUG and the Oregon Modeling Statewide Collaborative. So thanks to Brian and all his contributions. And if you haven't signed his retirement e-card, please do so. That was mailed out to the mailing list about a week ago. So be sure to watch for that. And then I don't know if there were any other updates from the group that we needed to share. If so, please speak up or raise your hand. But I wanted to be sure and thank Carol Richardson also for her help facilitating and organizing this event. Couldn't pull it off without you.
Thanks, Garth.
All right. Not hearing anything else. Everyone have a great day. And as noted there on the screen, this recording, as well as all the other OMUG materials, are going to be up there on the website. So you can catch that at oregonmodels.org. Thanks, everyone, and have a great day.